Muy buenas tardes para todos y para todas. Para mí es un gusto volver a presentar esto de los coloquios Ortiz Chardin. Los coloquios hacen parte de un proyecto general llamado el PPU, Proyecto de Planeación Universitaria, El Hombre en el Cosmos. Un grupo de profesores de aquí de la universidad empezamos a pensar, ¿por qué no pensar esas preguntas fundamentales? ¿Por qué no pensar sobre el origen del universo, el papel de la humanidad en el universo? Y hemos estado invitando una serie de personajes, filósofos, teólogos, científicos, que nos ayuden a resolver esta cuestión, a dar respuesta de qué es esto del hombre en el cosmos. Aquí tenemos varias actividades, ¿cierto? La más fuerte ha sido un seminario permanente de profesores, donde hacemos esas reflexiones. Invitamos varios profesores, cogemos un tema, le vamos dando vueltas, nos hacemos las preguntas, etcétera. Y a partir de ahí empezamos a generar una serie de documentos que nos ayudan a fundamentar esto de las preguntas, pues, que pueden ser importantes para nosotros. Dentro de ese proyecto hay un coloquio que se llama el Coloquio Ortiz Chardin y está basado principalmente en dos jesuitas, dos personas que nos ayudaron o nos empezaron a hacer esos diálogos. Por un lado está Carlos Ortiz, que fue un jesuita, hizo un doctorado en física en Zúrich en torno al electromagnetismo. Uno de los edificios, como ustedes saben, de aquí de la universidad lleva su nombre, Carlos Ortiz. Entonces, a partir de él empezamos, ¿por qué no hacer esos diálogos de filosofía, teología, ciencias? Y surgió todo esto de ¿por qué no un coloquio? Por otro lado está Talar de Chardin, él es, o fue más bien, un paleontólogo, tuvo que ver mucho con el descubrimiento del hombre de Pekín, uno de esos eslabones donde la antropología y sobre todo la paleontología ha estado buscando cuáles son los orígenes de la humanidad, cuál es ese paso que se da dentro de la evolución para que podamos conseguir la cadena de hombres y mujeres para poder llegar allí. Entonces, con el coloquio Ortiz Chardin, precisamente esto, invitar a personajes, científicos, pensadores que pudieran estar en la vanguardia de todo esto. Un tercer grupo, y aquí veo a algunos de los jóvenes, que está Astrojave. Todos los jueves, en una de las terrazas de aquí de la universidad, pues quisimos, ¿por qué no utilizar un grupo? Y empezamos a preguntarnos en torno a la astronomía, y se formó así el grupo de Astrojave, al cual están cordialmente invitados. Después, de pronto, Miguel nos puede dar su correo, etcétera, a ver cómo podemos ir vinculando más jóvenes a esta actividad. Y finalmente, pues, además de este coloquio del seminario, pues entiendo que nos están viendo de otros países, por eso empezamos 6 en punto, porque hay invitados de Alex, que allá sí es hora americana, no. Entonces, por eso he estado aquí dándole vueltecitas. Entonces, quisiera invitar aquí a los profesores, como que con los que empezamos a dar esta idea de los coloquios Ortiz Chardin. Entonces, invito al profesor Reinaldo, de la Facultad de Filosofía, y al profesor Alfonso Leiva, que también han estado ahí detrás de esto del PPU, Proyecto de Planeación Universitaria. Entonces, les doy la palabra aquí a los…
Tú primero. Ok, buenas tardes, buenas noches a todos. Estaba esperando a unos estudiantes afuera por el tema de la puntualidad y lo que teníamos, la lluvia ha afectado un poco la asistencia hoy. Aún así, muy feliz de estar aquí nuevamente, encantado de tener un invitado del perfil que tenemos esta noche y bueno, a seguir con mucho ánimo las actividades del coloquio, ¿no? Profesor Bernal.
Bueno, buenas tardes para todos, me alegra que estén acá. Va a ser una charla supremamente interesante y diferente de las charlas que hemos tenido antes, ¿no? Un tema que todavía no habíamos abordado. Entonces yo tengo muchas expectativas frente a la charla y le agradezco mucho al profesor su presencia. Bueno, entonces, eso.
Yes.
Si quieres,
Actually, tonight is the first talk in Spanglish, eventually Spanglish. In principle, is English, the official language of tonight. And this is the first activity in which we are going to switch to the international profile of our colloquia. And for that big event, we have tonight Professor Ely Kossovsky. He is from New York. Actually, originally, his family, grandparents, and so on, from Poland and Russia, and okay, some part in upstairs Europe. And he is actually a very interesting character. More or less the same situation as one of the Nobel Prize winner, who is not a professor. Clauser is not a professor. Yeah, not a full professor, not even an associate professor. More or less the same situation. More or less, you are doing also some teaching, yeah, but he is some academic independent freelance, more or less. Yeah, he is actually author of 5 books. And which is really interesting is that he is one of those characters who is doing mathematics, applied mathematics, on making money with mathematics. He is tonight going to speak about the Beard of Science. He has a very nice book here. And because of the profile of the PPU, we asked him to focus his talk in this big debate between Galileo, Tycho Brahe, and Johannes Kepler. But this is just one of the faces of Alex. He is also author of this other book. There is also a second edition, the Benford's Law. And with this Benford's Law, he is actually doing money. He has a patent, and the patent and the Benford's Law is applied to fraud. Él está usando matemáticas para descubrir la mentira en los números de corporaciones, en los números de compañías, de elecciones también. Many business possibilities, yeah. You are right now in the right country. Then you see, mathematics is not only to teach some calculus in the first and second year in some engineering department or something. And what else can I say? He has a patent. Yeah, the patent. US patent, yeah, for the Benford's Law. Then we are doing all this theater to show you that mathematics, science, basic science is much more than teaching calculus and mechanics in the first and second year. Okay, that's the central point of all this issue. And right now we are going to enjoy the talk, focus on his own book. We are very, very happy of having you tonight.
Thank you very much, Professor Alfonso and Professor Nelson. Shall I speak from here or from here? From here is better? Or from here? From there, okay. Okay, so let's start, students and professors.
Wait a second.
Empezar, ¿sí?
One of the other talents of Professor Alex is he speaks a lot of many, like 3 languages. And he's tried to speak some Spanish, some Spanglish eventually. Please feel free to ask at any time in any language. We are going to be supporting the communication.
Thank you very much. I will speak slowly. Voy a hablar despacio en inglés o en español, bien despacio y bien claro, así espero. I hope to speak clearly. Entonces, vamos a empezar la charla. The title is Mathematical Perspectives in the Emergence of Physics. prospecticos, de emergence es como la origen, como el proceso de descubrir, ese emergence, to emerge, to become, hacer. Mathematical perspectives in the emergence of physics. The 6 personalities responsible for the discovery of physics. Los 6 personalidades que ellos están descubriendo la física. Vamos a ver. Nicolás Copérnicos, the heliocentric model, que todos los planetas y la Tierra se mueve alrededor del Sol, que era algo nuevo casi. Bueno, Tycho Brahe, recording the most accurate and comprehensive astronomical observation. Recordar no era científico, la verdad, científico per se. Era como alguien que toma muy cuidadosos pruebas de los planetas, tiempo, posición y estos. René Descartes, debe ser René Descartes, francés, usted sabe, Modern Scientific Philosophy, the Cartesian XY Plane. El cálculo se basa en XY Plane, entonces tenemos que tener ese antes que Isaac Newton y Leibniz podía descubrir el cálculo. Johann Kepler, de Alemania, 3 laws of planetary motions, 3 leyes del movimiento de los planetas. Galileo Galilei, the father of science, el padre de la ciencia. Motion experiments on Earth, experimentos del movimiento aquí en la Tierra. Isaac Newton puse todo junto. Él tiene todo como todo está como arreglando, como está listo para poner todo en su cabeza. Modern Physics, 3 Laws of Motions, Universal Gravitations. Y él depende de los generación antes, que los científicos antes. Entonces, este es el proceso. Pero sumir, Kepler Celestial Data Analysis, Galileo Terrestrial Experiments, Newton's Grand Synthesis, Midwifing the Birth of Science. Partera el nacimiento de la ciencia. A ver, physics was humanity's first success in science. La física fue el primer éxito científico de la humanidad. Mucha gente no sabe esto, pero ese fue así. Significant progress, discoveries, and major breakthroughs in chemistry, biology, geology, economics, medicine, and other scientific disciplines all came after physics was discovered. Progresos científicos, descubrimientos y avances importantes en química, biología, geología, economía, medicina y otras disciplinas científicas se produjeron después del descubrimiento de la física. It is reasonable to state that the decisive success of physics in the 17th century gave inspirations and confidence to later actors in the sciences, that they should indeed investigate and theorize that there was surely something essential out there to be discovered, just as it occurred in physics. Es razonable afirmar que el éxito decisivo de la física en el siglo XVII dio inspiración y confianza a los actores posteriores de las ciencias, que si deberían investigar y teorizar, que seguramente había algo esencial por ahí por descubrir, tal como ocurrió en la física. In that sense, the intergenerational discovery of classical physics between Copernicus' publication of, it's in Latin, De Revolutionibus Orbitus Coelestium, no sé, mi padre podría hablar latín, and in 1545, and Newton's publication of Philosophia Naturalis Principia Mathematica in 1685 can be thought of as the birth of science. Porque antes no teníamos nada, no teníamos ciencia, la verdad. no teníamos nada. Este era el principio, el raíz de la ciencia física. En ese sentido, de descubrimiento intergeneracional de la física clásica entre la publicación de Copérnico en 1543 y la publicación de Newton en 1687, se puede pensar como el nacimiento de la ciencia. Ok, vamos a volver más el tiempo más antiguo. Greek Hellenic culture, cultura helénica griega. Focus on beauty, harmony and symmetry. Concentra en la belleza, la armonía y la simetría, así como es. Focus on studies, debates and abstract thinking. Concentra en estudios, debates y pensamientos abstractos. Rafael era the Renaissance painter in Italy, School of Athens. Ancient Greece had a strong influence on matter of astronomy, mathematics, and geometry, but less so on science. No, el antiguo Grecia no era muy fuerte en la ciencia. ¿Por qué? Porque si tiene el astronomy, mathematics, geometry. Bueno, the Great Library of Alexandria in Egypt was one of the largest and most significant libraries of the ancient world. It had about 200,000 scrolls, books. Es una librería, no, biblioteca, no sé, biblioteca. Lo más grande en este tiempo, no hay un foto aquí, pero eso es. Ahora, vamos a pensar, ¿qué pasa con antigua Grecia que nos ha dado geometría? Geometría es greca, ¿no? ¿Sí o no? Geometría es, geometry is Greece, we know that. ¿Pero qué pasa? ¿Qué errores tienes? Three erroneous ideas of ancient Greece. 3 ideas erróneas de la antigua Grecia. 3. Primero, celestial immutability. The heavenly bodies were considered to be eternally unchangeable. Es que nunca tiene cambio, la luna, el sol, los planetas, estrellas, no, nada, no, es para siempre, así para siempre, sin cambio, eternamente. But the planets, the sun and the moon are physical entities, we know. Hence, they undergo change. Es algo físico, entonces se cambia en tiempo largo. The second error, el equivocado segundo, celestial perfection. Celestial objects were considered to be of perfect spherical shapes, perfect circular orbits, beautiful, without spots or blemishes. Como son, el círculo es esférico, es perfecto. Y el movimiento es un circular. Es y muy bonito, belloso sin nada, perfecto. Algo así. Circular movimiento y esferical. But celestial objects are physical entities, so they are not perfectly looking. The moon has hills and valleys. The sun has sunspots and so forth. Also, the mathematical implication of physical law create odd and uneven orbits, such as conic sections, ellipses, parabolas, hyperbolas. Entonces, estas cosas en cielo son algo físico, entonces no es perfecto. El tercer error, el tercer equivocado, era el geocentric model. Todo está en movimiento alrededor de la Tierra. Somos el centro del universo. The geometric model is summarized by the Greek astronomer Ptolemy, is based on the notion that the planets and the sun revolve around the earth. Somos la Tierra, es el centro. Todo, el Sol y la planeta, todo se mueven alrededor de la Tierra. Es equivocado. Este no es correcto. These three dogmas held back progress in science. Humanity had to overcome this. It overcame this about 2,000 years later during the Renaissance era. Estos tres dogmas impidieron el progreso en la ciencia. La humanidad tuvo que superó esto unos 2000 años después, durante la era de Renacimiento. The Renaissance, el Renacimiento. Nicolás Copérnicos, The Heliocentric Revolution. Ahora, todo están moviendo alrededor del Sol. El Sol es el centro, heliocentric. Las planetas y nuestro planeta Tierra. The heliocentric model hints at gravitational force of the sun acting on the planets. The sun holds the planets together, pulling them inward. But it's only a clue. Es solo una pista. A ver, es que si tiene este modelo, no tiene física o teoría, es solo un modelo, pero es una pista que el Sol tiene algo que ver con esto movimiento. Está como, it's pulling it inside, it's calling it in. Galileo Galilei, the father of science, central figure in a Renaissance era transition from natural philosophy to modern science. Galileo generic contribution to physics and science. Empiricism for philosophy of science, namely the scientific method. The rejection of highly abstract philosophical argument about the world without experimental sensory data. Entonces, como sabemos el mundo no por solo puro pensamientos abstractos, tenemos que verificar, tenemos que hacer experimentos, no solo pensar. Solo pensar sin ver y chequear no es suficiente. Este era algo nuevo, estamos acostumbrando, por esta época era algo, una idea como revolucionario. The adoption of mathematics and geometry as essential tools in science, usando matemática y geometría para aprender el mundo. Era algo también nuevo. The four principal contributions, entonces, esto era algo general, como filosofía, la actitud, the approach, the general philosophy. Ahora, hay cuatro cosas más concretos. The four principal contributions of Galileo to the core concern of physics, namely to the study of motion. Cuatro cosas más concretos en el corazón de física. La cosa es que más importante es teoría de movimiento o de estudio de movimiento. Física es movimiento, la verdad, piénsalo. Vamos a ver cuatro cosas. Primer, horizontal inertia. Segundo, proper definition of acceleration as the change in speed per change in time. Podría ser algo diferente, como the change in speed per distance. Es muy confundido. Ahora estamos acostumbrados, cuando tiene una clase de física, pero es algo que Galileo Galilei abrió la puerta para nosotros, para entender. Esa es la vía de entender. Vertical free speed acceleration is constant and independent of weight mass. Entonces, algo como eso. Dos bolas en tower, the leaning power, dos bolas, una muy pesada y una liviana. One is very heavy and one is very light, and they all came down at the same time, same speed, I guess. And everybody was surprised because they expected the heavy ball to come first and after the light ball, but no. Now, entonces, number tres, vertical free fall acceleration is constant and independent of weight mass. Constant also, it doesn't change, even one ball. Aún una bola, una roca, lo mismo acceleration siempre, no se cambia. the splitting of projectile motion into its inertial-like and constant speed horizontal component and free fall accelerating vertical components. Entonces, dividir el básquetbol o pues una pistola, una bala que es así. Vamos a hacer un análisis, una separación, el movimiento horizontal y el movimiento vertical. Nadie estaba haciendo eso antes de Galileo, esa es la idea de Galileo. ¿Y qué podría haber? Chequea esto, que horizontal es constant speed, lo mismo velocidad, y vertical es lo mismo como así, como algo que está como así, solo puro vertical. Si este paso dice que es it's a legend or a myth, no sabemos qué era la verdad, pero es una cuestión. Pues no era la verdad, pero era idea. The heliocentric model was passionately supported by Galileo, who risked his life defending it. El modelo heliocéntrico fue apoyado apasionadamente por Galileo, quien arriesgó su vida defendiéndolo. Aquí está Galileo allá en Pisa o en, no sé en dónde, en Italia. Galileo then gave the heliocentric model decisive confirmation with his telescopic observations of Jupiter's 4 moons and the phases of Venus. Phases of Venus es como la luna, pero no es la luna, es una planeta. Si tienen telescopio podría ver, es como está moviendo alrededor del Sol, no alrededor de nosotros, la Tierra, no. Y Júpiter tiene Júpiter tiene 4 lunas y podría verse, están como así, podría ver que están alrededor del Júpiter, no nosotros. Clearly, Venus and Jupiter's 4 moons do not move around the Earth. Claramente, Venus y las 4 lunas de Júpiter no se mueven alrededor de la Tierra. Es algo muy fuerte, muy claro. Entonces, the geocentric model was now rejected by Galileo observations by most astronomers. El modelo geocéntrico ahora fue rechazado a través de las observaciones de Galileo por la mayoría de los astrónomos. Es algo muy fuerte. Y ellos también podrían tomar un telescopio y ver bien claro. Entonces ya, está rechazado. Geocentric model, muy importante. Ahora, es muy interesante para los físicos, pues. It's interesting for physicists to notice Galileo's extensive observation and careful studies of the sky, very famous, with his telescopes, were not related directly to pure physics, namely not related to the study of motion and the laws of nature. Las extensas observaciones de Galileo y los cuidadosos estudios del cielo con sus telescopios no estaban directamente relacionados con la física pura, es decir, no estaban relacionados con el estudio del movimiento y las leyes de la naturaleza. Galileo physics work was with experiments here on Earth. This was his contribution to pure physics. La obra de física de Galileo fue con experimentos aquí en la Tierra. Yeah, we all know that Galileo had a telescope and yay, but it's not directly related to physics. Okay, es algo curioso, something curious to know. The theological scientific issue, el conflicto teológico asunto. Bueno, the 10 Commandments, los 10 comendamientos, en español aquí. The Hebrews' original discovery of monotheism, the existence of one God, or the oneness of God. El descubrimiento original de los hebreos del monoteísmo, la existencia de un Dios, la unidad de Dios. In a sense, physics was inspired by the idea of monotheism, always searching for unity, unification, simplicity, and for generality in laws having the widest scope. Es como monoteísmo. En cierto sentido, la física se inspiró en la idea del monoteísmo, siempre buscando la unidad, la unificación, la simplicidad y la generalidad de las leyes, que las leyes tienen el más amplio alcance. For example, Albert Einstein efforts towards the unification of the four forces. It is tempting to ask, if only four, then why not one? This is the tendency in physics to always unify, to simplify. So if you have 7 gods, why the Greeks had so many gods and the Romans before? One God, one force, one God, one force. Okay, now in 1633, Galileo was accused of writing against the Bible. Ahora, en 1633, Galileo fue acusado de escribir contra la Biblia. According to Pope Urban VIII and the Inquisition, the Bible contradicted Galileo. Según el Papa Urbano VIII y la Inquisición, la Biblia contradijo al Galileo. Pope Urban VIII, Maffeo Vincenzo Barberini, disculpa, the former friend and strong supporter of Galileo, was offended by the way Galileo published his book, Dialogue Concerning the Two Chief World System. Galileo tiene una promesa para tener los dos vistas del geocentric and heliocentric, pero Galileo no pude ser como neutral, no pude. Entonces puse cosas contra la otra modelo. The Bible was utilized as a tool against Galileo. It was done by twisting the figurative language into literal language. La Biblia fue utilizada como una herramienta contra Galileo. Se hizo torciendo el lenguaje figurativo en el lenguaje literal. Vamos a ver. La Biblia, the Bible, Genesis, y vamos a ver en Ecclesiastes. Well, the words of the teacher, son of David, king in the Jerusalem, vanity of vanities, said the teacher, vanity of vanities, all is vanity. What do people gain from all the labors which they toil under the sun? One generation passes away and another generation comes, but the earth remains forever. The sun rises and the sun sets, and to its place it tends again, it rises there. Aquí en español, palabras del maestro, hijo de David, rey en Jerusalén, vanidad de vanidades. Pero mira, pero la tierra permanece para siempre. El sol sale y el sol se pone, y en su lugar tiende de nuevo. Ahí sale. Ahora, Salmo es más claro. Es casi contra el modelo de Galileo. The Lord set the earth on its foundation. It can never be moved. Psalms 104:5. El Señor asuntó la tierra sobre sus cimientos. Nunca podrá ser movida. This is the Galileo's trial in Rome, 1633. Es un dibujo muy famoso. And yet it moves. Yo no sé cómo decirlo en latín, pero dice al fin, pero en silencio. No, en un voz muy bajo. A superb account of this theological scientific drama was written by the late historian Giojo de Santillana, The Crime of Galileo. I read the book from beginning to the end. It's a fascinating book. I recommend to read The Crime of Galileo. I think it's in English, but you might have it in Spanish, I'm not sure. In 1757, the church has removed Galileo's dialogue concerning the two-world chief world system from the index of its list of banned publication. So one good step of the Catholic Church. In 1992, more than 350 years after the Roman Catholic Church persecuted Galileo, Pope John Paul II formally rectified the church error. Entonces, ya estamos en una época diferente. We totally know that Galileo was right in adopting the Copernican astronomical model, say Cardinal Popard, the director of the new investigation committee regarding Galileo's work. And of course, this is 1992. Lesson to humanities. You have jailed your first physicist. It's not good. You have condemned him to be surrounded by Inquisition soldiers for the rest of his life. Free speech is essential. Yo escucho mucho aquí que en Javeriana free speech es muy importante, es parte de la cultura de Javierana, Universidad Javierana. Lección para la humanidad. Has encarcelado su primer físico. No es bueno, no es bueno. Lo has condenando a estar rodeado de soldados de la Inquisición por el resto de su vida. La libertad de expresión es esencial. Tycho Brahe, de Sweden, Norway, Sweden, Denmark, the meticulous celestial recorder, the Swedish-Danish astronomer, known for his highly accurate and comprehensive astronomical observations regarding planets' movement. King Frederick II of Denmark gave him an island to do observations. Here it is, between Denmark and Sweden. It's an island. And Tycho built an observatory in 1579 and made many naked eye without telescope, no telescope. Here it is, the picture. Tycho collected an astounding amount of astronomical data, writing down the location of stars and planets in the sky and the associated time of observations. Now, another figure from Germany, Johann Kepler, considered the first data analyst by many. In 1955, Tycho was warmly invited to Prague by Rudolf II to build his second castle to observe the sky. As soon as Tycho settled in Prague, he invited Johann Kepler of Germany, who came there in 1600. Tycho needed an assistant, someone with good mathematical talents and good knowledge in astronomy to work on his data. Como hacer análisis sobre el conjunto de data que tiene Tycho. Pero Kepler era un poco joven para eso, pero it was an amazing, successful selection of an assistant. Kepler was perhaps the only person able to make real discoveries from Tycho's data. Rare coincidence, pues realismo mágico. No sé si Gabo está de acuerdo conmigo, pero pues es así. Porque la verdad, sin saber, yo no conozco toda la gente que vive allá en Europa en esta época, pero estoy casi seguro que cualquier otra persona que está invitado no pude descubrir 3 leyes de los planetas, solo Johann Kepler. ¿Y cómo sabía él, Tycho Brahe, invitar Kepler? Interesante. The relationship between Tycho and Kepler was often tense and conflicted. They had several angry exchanges, arguments, and disagreements. Está un poco como una relación duro, es como discusiones. They finally came to agreement, and Kepler came to settle in Prague and started to work on Tycho's data. Tycho refused to give Kepler enough data. Tycho did not trust Kepler with all his data. So he's inviting him to come to help, but he's afraid to give Kepler all the data because the data was his life work. His whole life work was the data, so he gave him a little bit. Kepler had access only to very limited data, but Tycho Brahe could not give all his life work to Kepler. Kepler could not discover anything. He tried. Science could not progress. Because if Tycho doesn't give Kepler the entire data, how can you work? You can't. Fortunately for science, Tycho suddenly died. Se muere. His death was probably caused by burst bladder. Well, Tycho offered a feast, una fiesta, una reunión with some honorable important guests. Muy importante invitados, como, no sé. And had refused to leave the feast to relieve himself in the bathroom because he would not have, it would have been impolite. No quería ir al baños porque estaba pensando que es descortés, pero era muy duro y ese es muy peligroso para tu salud. After he returned home, he was no longer able to urinate almost and he died within 11 days. Si usted no va al baños muchas horas, es peligroso, usted podría morir. No sé, hoy es diferente. So in 1601, Tycho Brahe, gravely ill, and on his deathbed, hands over to Kepler the most accurate planetary data in history, the entire data, todos los conjuntos de datos de todos los planetas, porque él sabía que ya va a morir muy pronto, sabía que va a morir, y si por lo menos dar al Kepler para seguir el trabajo. Now science can progress. Ahora la ciencia podría tener progreso porque Kepler tiene todo el dato y libertad para hacer como quiera con el dato. Libertad, investigar y hacer análisis de data. Kepler then formulated his 3 planetary laws over the following years after tedious calculations and persistent search for patterns in the data. Kepler's first law. Okay, first law. The orbit of a planet is an ellipse with the sun as a focal point away from the center. Ellipse tienes dos ojos, 2 eyes. The ellipse has 2 eyes, and one of the eyes is the sun, not in the center. It's not a perfect circle. No, it's not perfect. It's not ugly, but it's not perfect. It's not a circle. Kepler's second law, the planet speeds up when you near the sun and slow down while you're farther away. Entonces, si es muy cerca del sol, es más rápido, más fuerza, más fuerza del sol, y si es lejos, es más lento. Kepler's third law, the square of the time for one full orbit is equal proportional to the cube of its distance from the sun. Es muy simple. El tiempo, el periódico de una revolución entero, potencia 2 igual K, proporción, la distancia del Sol, del planeta, potencia 3. Es decir, otra forma que Mars square the time divided by distance cube of Mars is the same in all the planets. Is always the same, is K. Este era muy duro, toma 10 años para descubrirlo, 10 años para descubrir esto, era muy largo, muy duro. The value of K depends on the scales, units, escalas, unidades. ¿Qué es D? Well, D es el promedio entre máximo y mínimo. It's a good compromise, okay? Kepler third law statistically. Okay. ¿Cómo sabía? ¿Cómo podría ser este tercer? Este hecho, distancia del planeta, pero Uranus, Neptuno, Pluto no está descubriendo esta época. No sabían, solo de 6. Tiempo, la Tierra, 365 días. 365 days for Earth, yes, for the time. Ok, aquí están, algo así. Discovery time, Mercury, prehistoric time, Earth always. Uranus no, Neptune no, Plutón no, todavía no. Era 1610 antes. Entonces, Kepler tiene solo Mercury, Venus, Earth, Mars, Júpiter, Saturn. Este tiene Y de usted podría conseguir la ley, el tercer ley, the third law, that if you cube the distance, you get times square. How do you get that? From this, only from this is the beginning of physics. El raíz de física, de 12 números o 6 puntos del data. Es muy interesante. A ver, entonces, 6 points consider the seed of modern physics. Well, it takes somebody like Kepler to get into fruition. No charts. René Descartes invented the chart few years later. Entonces, Kepler no tiene la idea de chart, graph. No tiene graph, no tiene chart. Pero vamos a ver. Entonces, no tiene. Pero eso es así. Ahora tenemos, pero él no tenía. Luckily, Kepler did not know anything about statistics. Es bien suerte que él no sabía de estadística. No regression, no logistic, no eso. Don't do it, Kepler. Don't do the regression analysis, please. Don't try to get parameters and stop there. Instead, look for more profound and more exact result. Okay, now, let us attempt to transfer the two variables so as to obtain a linear relationship. Linear relationship? Why? Because linear relationship would imply some simple predictability. Queremos una línea de este chart. Ok, vamos a ver. El 12 números, 6 puntos de data, el ratio, dividir tiempo, dividir la distancia, está creciendo. Entonces, ¿qué hacemos? ¿Por qué está creciendo? Time is growing faster. Tiempo está creciendo arriba mucho más que distancia. Entonces, por eso. Entonces, time es como explotando. Distancia es más suave. Vamos a ayudar distancia. ¿Cómo ayudar distancia? Bueno, potencia 2. Hace una ayuda, pobrecito distancia, porque distancia no está creciendo tan rápido. Entonces, time está creciendo muy rápido. Entonces, ayuda a distancia. Potencia 2. Bueno, hagámoslo. No, es demasiado. Ahora distancia es mucho más rápido que tiempo. Exagerando. Bueno, pero entonces vamos a hacer esto. Cada una, tiempo y distancia, tener potencia. Pero un poco más potencia a distancia que tiempo. Distancia, regalamos un regalo de 3, potencia 3. Y tiempo regalamos potencia 2, un poco menos, para hacer balancia. Así, sí, perfecto. Mira, una línea, perfecto. Entonces, sabemos que distancia tiene desventaja y el tiempo tiene ventaja. Entonces, hacer una corrección, balancia, contra potencia 3 a distancia, potencia 2 a tiempo, y perfecto. Y esta es la ley. Power law relationship. Esta es la ley que es constante. El K, la letra K. Pero vamos a ver otra vista. Kepler's law, third law, logarithmically. But the supposed process of discovery outlined above was not the way Kepler actually worked it out. No, esa, era diferente. Pythagoras was interested in the connection between mathematics and music, and this would lead to the third law via logarithmic. This is Pythagorean tuning, es algo de música que pertenece a matemática, tiene como algo de tres mitades o 3 medios. Pythagorean tuning is a system based on going up and down from 3 to 1.5. For the ancient Greeks, integral whole numbers presented beauty, perfection, and harmony of sound as well, music. Kepler in search of the harmony of the planets. Kepler have been decisively aided by the recent mathematical invention of logarithm, just a few years before his discovery of the third law. John Napier and Jules Bourgi, they wrote about logarithm in 1614. This is one book. It's in Latin. At that time, the world between countries did not communicate in English. It was not the international language like English now. It was Latin. Latin was the language of the scholars, of the academics, between England and Russia, between Russia and Italy, between Italy and Germany, etc. Kepler was well aware of the logarithm. He actually communicated with them. And now let's change the law and let's take the log. Take the log. This is the third law, right? The third law. T to the power 2 equal k d to the power 3. Tomando el logaritmo a los dos lados, la izquierda y la derecha. ¿Y qué tenemos? If you change to log, you have a linear relationship with a slope of 3/2. Ah, a ver. Hence, Kepler's third law asserts that the log transform data was a simple linear relationship. Slope is 3/2. Ejemplos, this example, distance, change to log, time, change to log, transformation. And now, if you look at two planets, planet A and planet B, take the log, según el tercer ley de Kepler, ¿sí o no? Tiene el slope 3/2. This is the third law in logarithm. This is the third law. This is how he discovered originally. He didn't write like that. This is the third law. Or the change in log of time divided by the change in log of distance is 3/2. It's that simple. Vamos a ver. Esto es. Entonces, ¿qué hacemos aquí? Tenemos distancia del planeta desde el Sol, tiempo de un periódico completo. Se escribe así en logaritmo. ¿Y qué pasa? Es una línea casi perfecta y el slope es 1.5 o 3 mitades, 3 medios. Postmortem triumph, the entire solar system, todos los planetas que sabemos, eso es. ¿Dónde está la Tierra? Ah, sí, azul. ¿Dónde está Colombia? Bogotá, no sé, está allá. Pero todos los planetas son así como casi perfectamente en línea. Pero por eso tiene que tomar logaritmo primero de la distancia y del tiempo, y así es. Y the slope is 1.5. So it's not, it doesn't, it's invariant, the scales. It doesn't matter, it's scale invariant. It's not music, they're not related to music. The mathematics of the physics just happen to lead to this 3.5 ratio of the slope, but it's not music, it's not harmony, it's just the mathematics and physics. Okay, another thing is that if you don't have a computer or calculator, si no tiene computadora ni calculadora, ¿cómo hacer? Tienes que hacer, Kepler tiene que hacer mucha calculación, okay? So, muy fácil con logaritmo hacer calculación. To Kepler, the discovery of logarithm were a gift. Logarithm speed up is arithmetic calculation. Es que tiene que hacer mucho aritmético como segundo grado, el primera escuela. Él tiene que hacer muchos, todos los días, muchos, horas y horas, y será muy difícil, sin duda. Pero con tablera de logaritmos, es muy fácil. Es muy fácil, así está. ¿Por qué? Porque multiplicación de dos números podría convertir a adición. Y división, que es muy difícil, es minus. Logarithm allow the conversion of difficult multiplication and division into simple addition and subtraction. En ejemplo, yo no quiero gastar mucho tiempo de eso, pero el ejemplo es eso. Es un ejemplo. Es muy difícil, si usted tiene que hacer ahora en una papel y Escribirlo ahora es muy difícil con un lapicero en papel. Pero vamos a ver, si hagamos, no voy a ver, pues, con logaritmo es muy fácil, boom, y ya está. Está. Este parece difícil, pero yo no quiero ver. Voy a enviar en correo electrónico a todos ustedes si quiero ver. Pero que es muy duro, la verdad, podría ser en tableras de logaritmo. No es difícil, yo explico, es muy fácil. Subtraction, addition, subtraction, and you get the answer. This is the answer. Entonces también logaritmo, mucho ayuda, muy importante para Kepler descubrir el tercer ley del planeta. It was very important for Kepler to use the logarithm tables to do the arithmetic calculations, which was very tedious, very difficult, and time-consuming. Now let's look at the implication of Kepler's Kepler third law to the speed of the planets. How fast do planets move? Well, this is the Mars. Is the most eccentric, but it looks like a circle. Es que el Sol no es el centro, solo esto. No, Mars no es lo más, pero es Mars. Mercury es lo más excéntrico en todos los planetas, pero todavía parece casi como un círculo. Ese es Mercury, ese es Mars. Es lo más, no es. Este es ellipse, pero parece como un círculo. Entonces, the sun is not at the center. Approximately 2 pi r. 2 pi r, circumference of that. El tercer ley es esto, resolver para tiempo. Take the square root to solve for t. And so put together, the speed is put together this, the blue, the green, put together, and this is the speed. This is the speed inversely proportional to the square root of the distance. Si es muy lejos, es más lento. La velocidad es más lento. Well, according to the second law, the planet speeds up and slows down, but approximately is correct. Entonces, aquí son los planetas. Fast Mercury, very slow Saturn. Vamos a ver estos en kilometers per day. Wow. Estamos moviendo el Earth, la Tierra, 2.500.000 y algo kilómetros cada día. Wow, muy rápido. Así es. Entonces, lejos es más lento. The inner planets, Mercury and Venus, near the Sun, very fast. The outer planets, very slowly. The Mercury and Venus closer to the Sun have the effect of gravity. It's a hint, es una pista de gravity. Jupiter and Saturn are farther away from the Sun, and thus the effect of gravity is less pronounced. Okay? This hints of the gravitational force is real, and it's correlated with closeness to the Sun. Este es una pista que el Sol, que está muy cerca del Sol, tiene que mover muy rápido para evitar la fuerza de gravity. Pero si está lejos, la influencia del Sol, de gravity, no es tan fuerte, entonces no necesita una velocidad fuerte para cancelarla. Kepler gravitational view. Kepler was the first thinker to hint at universal gravitation. He said that the sun is moving mortixem animam, moving soul for the planets. But for the scientific community, it sounds like superstition or magic. They didn't believe in that, but it was true. It was true. But Kepler wasn't afraid to write that he thinks that the sun is responsible for moving the planets. And they say, no, that's ridiculous, but it was true. Okay, René Descartes, the Cartesian coordinate system, 1673, after the third law, after the planets. X and Y. nosotros no podríamos creer que como 400 años, 450 años antes, en pasado, no teníamos chart, no teníamos graph, ni uno, nada. Así es. Cálculos, está necesario por cálculos. Entonces, we are helping Isaac Newton to prepare calculus, and also Leibniz. Analytical geometry is based on the X and Y. So yes, that was René Descartes. Finally, the last personality is Isaac Newton, and he puts the Galileo terrestrial experiments, Kepler celestial data analysis together, grand synthesis. Let's look at the basketball. The basketball is horizontal inertia, vertical acceleration. Earth gravity is not suspected as a cause, so Galileo is a little bit confused, but it gives a hint to Newton. Let's look at Kepler. Kepler differentiated speed. Doesn't matter what the speed. He didn't know the mass of the weight of the planets. So obviously some planets are heavy, some are light. It doesn't matter. Like Galileo. Galileo dropped two balls, one heavy, one light, one big, one small, and it doesn't matter. It's interesting. Faster near the sun, slower when far away from the sun. The sun is suspected as the cause of gravity. Put it together, Newtonian synthesis is that the planets move and the basketball move, but the planet moves under the sun gravity in the same way, the same physics. La física es lo mismo, lo mismo. Basketball o planeta es lo mismo. The planet moves under the influence of Earth gravity. The basketball moves under the influence of Earth gravity, and the planets moves under the influence of sun gravity. That was the idea in the mind of Newton under the apple tree at the age of 25 years. Yeah, so we will unite, again, unity. We will harmonize the movement of the planets with the movement of the basketball or the cannonball. Newton grand synthesis, the unification of the heavens and the earth. Ball projectile motion, planet projectile motion. Inertia in all direction, unless force is present. Universal gravitation as a force leading to acceleration. And he published his book, Principia, 1687, in Latin. Oh, he was also in English later, I guess, I don't know. First law, second law, third law. I don't want to spend time on it because I'm sure all of you know the law, if not from the university, from high school, colegio. Universal gravitation, okay. G is a constant. I don't want to spend time on that. And let's continue. Here is Newton, 25 years, 25 años, muy joven. Pero ¿era la manzana o no? Was it really just an apple? No, not really. It was also the large set of planets. A typical star has an average only one or two accompanying planets. So, generalmente, las estrellas tienen solo uno o dos planetas, no más, no hay muchos. Solo como 10% de los planetas tienen muchos, 10% de las estrellas tienen muchos planetas, como nosotros, tenemos 8 o 9, no sé, pues 10, pues 11, pero estamos muy como bendición de muchos planetas. Si tenemos solo una planeta o dos, no. Apparently, the abundance of planets around our star is a bit rare in the cosmos. Es un poco raro en el universo, el cosmos. The planets had played the first provoking role. Pensar. Los planetas, la existencia del planeta era muy importante para la física. By being the only frictionless and smooth system of phenomena we human could have observed back then, and possessing near perpetual motion, a fine manifestation of the principles of inertia and gravity combined. Si usted va a la tienda, como hielo, hacer como skating, ice skating. Well, ice skating is inertia and no gravity. But see, planetas tiene gravity, inertia, combined. A ver, planeta, el Sol, the planet and the sun, gravity and inertia is perfectly balanced, Perpetual motion machine. There's no need for fuel, energy, diesel or gasoline. No necesitamos gasolina. I don't know, true long term, the system eventually loses energy via gravitational waves. Does it stop? You physicists know more about it than I do, because eventually you lose energy. I don't know. But basically in the beginning, it's a perpetual motion machine. See, do you need energy? No. Do you need a machine? An engine? No necesita una máquina, un motor, no necesita nada. Así se mueve, sin fin, perpetual. Una máquina de movimiento perpetual. The planets had played the second provoking role by being the only phenomena with clearly differentiated forces and differentiated resultant accelerations we humans could have observed back then. Okay, so different planets, they have different speeds because they have different force. This gives the hint of force, and that the force is far away, is less, is going down, divided by r square, is diminishing, is slowing down. Entonces es una pista que es. Without the planets, si no teníamos planetas, Kepler laws would have never been discovered, of course. Newton might not have his grand insight, I don't think so. Without Kepler's law, no. And humanity's progress in science would have been slower. Por el hecho que tenemos muchos planetas y Kepler podía llegar a 3 leyes de los planetas, el joven Newton de 25 años tiene la pista. Otras pistas de Galileo, sí, los dos. Pero sin planetas, si tenemos solo 1 o 2 planetas y no tenía la ley de Kepler, no teníamos Newton, no teníamos Principia. La física va a llegar, pero más tarde, un atraso grande de 100, 200 años, no sé qué va a pasar. Pero la planeta da a la humanidad la pista de física, gravitación, ok, la pista. No solo era la manzana, parece muy deliciosa para mí ahora que tengo hambre, pero no, esta la manzana era también la manzana, porque la manzana, por Galileo, los experimentos de Galileo eran manzanas, aquí la Tierra, pero mucho ayudo del Kepler que tiene este cosa. Este es una pista muy grande, muy importante. Ok, ahora todavía tengo tiempo, entonces voy a hablar de otra cosa totalmente diferente. Entonces usted puede como hacer esto y levantarse, otra cosa diferente, casi diferente. Bode's Law, la ley de Bode. Bode era un alemán astrónomo que está en el sistema solar. Esta es la distancia de planetas, Mercury, Venus, Earth, Mars, Jupiter, Saturn. This is the positions. ¿Usted puede ver algo raro o todo está bien aquí en la Tierra? 10. Saturn. Yeah. Bode question, la pregunta de Bode. Why are the planets' positions around the sun as they are? Bode answer, let us fit the 6 planets into a mathematical expression. Entonces, ¿por qué es esto? ¿Por qué? Que vamos a hacer una explicación. Yo no voy a aceptar ese así como es. Voy a hacer una matemática, una fórmula. It was a data analysis, no, era más como un análisis, analista de datos que un astrónomo. Ok, now hacer, a ver, it triples each time, you multiply by 3. It jumps by 33, you add 7. It shrinks by 50%. Multiply by 0.5, well, let's see. 432, 432, 432, que 43, 432. La distancia es esta fórmula, tan fácil. 4 plus 3 por 2 potencia n. ¿Qué es n? Depende del planeta. Primer planeta es minus infinity. Después 0, después 1. Un poco raro, pero no tanto. No tanto. Entonces, esto es la distancia. Dice ese Bode. Cada planeta tiene 4 plus 3 por 2 potencia. Depende. Minus infinity, 0, 1, 2. Hay una planeta entre Mars y Júpiter y Saturn. It's excellent, but you need una planeta. Es una planeta de escondida. Es una planeta que usted no puede verla. Pero si ponga este planeta, todo salió muy bien. Entonces, ¿por qué no? Vamos a poner este conjunto de data, 6 puntos, a esta fórmula. Bueno, es perfecto. Sí hay una planeta entre Mars y Júpiter, y sí, parece que sí, porque hay espacio allá. Hay una planeta escondida entre los primeros 4 y los otros 2 allá. Ok, entonces, era interesante, pero ¿cuál planeta escondida? Es un poco raro. Tienes que creer en este. Ahora, Uranus era descubierto en 1781 y sí está bien con la fórmula, pon la 6. Ahora vamos a buscar este planeta escondida en cielo, ¿dónde está? Y sí, ellos tienen como Celestial Police buscando en este lugar. Y sí, de Asteroid Belt en 1801, Ceres. Perfecto. Ahora, y aquí Ceres, aquí todo está bien. Ceres, Júpiter, Saturn, Uranus. Así es. Ahora, esta era la ley de Bode. La ley de Bode. Parece muy bien, muy bonito, ¿sí? Pero ¿es correcto o no? Vamos a ver. Now, todos los astrónomos tiene fe en la ley de Bode, tiene fe, mira, no es perfecto, pero es muy bueno. The fit is very good. No, please keep an open mind, keep you intact, your healthy scientific skepticism. Suddenly, bad news strikes. Neptune was discovered, and many years later, Pluto was discovered, and not good. It doesn't fit. Entonces, no vale nada, trabajando para nada, porque ahora tenemos 2 planetas que no están. Pero por supuesto, ¿cómo puede buscar una fórmula exacto para un proceso aleatorio? Both for us apart. Clearly, Bode's law is just a mathematical coincidence, not law of nature. But, ¿cómo podríamos descubrir este planeta escondida en el cielo? ¿Ceres? Sí, podríamos, no es necesario. ¿Cómo vamos a hacer el espacio entre eso? The hint is the ratio. Statistically, it is the ratio. Entonces, 1.5, 1.9, 1.4. Después tengo 3.4. Entre Mars y Júpiter, algo raro. Entonces es outlier. Este es outlier. Abnormality. It's a quantum jump. Missing planet. Es una planeta, falta una planeta. Porque falta una planeta. Vamos a buscar. Es muy obvio, si usted ve el Sol, los planetas entre el Mars y el otro es un gap, como falta algo, falta espacio, no hay nada. Let us calculate the ratios. Okay. The ratios are here, divided by 7, average is 1.6. Approximately every planet, next one is 1.64, 1.64, 1.64. So average ratio is 1.64. So distances are increasing by 64%. Okay, let's go forward from Mars o backward. Podríamos decir adelante del Mars o atrás del Júpiter. Adelante de Mars es esto, 25. Atrás de Júpiter es 31.7. Promedio, the average is 82.3. And wow, it's correct. So actually we don't need Bode's law. We can do it in a statistical way, reasonable, and the hidden planet is 28.3, which is correct. We will find it is correct. Now the ratios are good. Logarithmic perspective of Ceres. We take the distances and we look at the logarithm. So here's the logarithm. Si no hay Ceres, es como este niña, si no tiene dientes. Si Ceres, todo está bien, pero si quita el Ceres, el logaritmo podría ver cosas en data de mundo físico o economía que no puede ver, pero tienes que, you have to transfer all your data to the logarithmic scale to see things. General note from data analysis, typically significant insight could be gained and new essential pattern revealed by plotting the graph of the logarithmically transformed data. It's very important sometimes to look at the logarithm data. We saw that in the beginning, from Bode's law, in the beginning, let me see, in the beginning. Okay, so here it is. This is, if you don't transfer logarithm, that's what you see, but you don't see much. You don't learn much. This is the original raw data. Dato conjunto original, crudo. But now we'll jump to that. Ahora sí. This is better. It looks visually better. So it's good to use the logarithm transform data. In conclusion, the discovery of Ceres could be independently made. The misguided approach of Bode's law. Planetary distances are random, not deserving of deterministic formula. A random process of the formation from the nebula and the space of gas and particles form the planets. The big fish eat the small fish. So gravity is like a big fish, big planet, big chunk of matters they eat. So you can't have two planets next to each other. One will eat the other. You need distances. So random planet formation means that you have distances. You can't have two planets next to each other. The big will eat the small. Gravity. Random gravitational forces ensure that things are very near each other, would eventually merge into a single planet. Reunir. Okay. Surely some misguided scientists would attempt to rescatar Bode's approach con otra fórmula y puede tener muchos éxitos. Sí, tengo una fórmula nueva muy bonita, pero no, es aleatorio, it's a random process. So I will say in English, there is some exceedingly valuable and generic lesson to learn from the story of the success and failure of Bode's law, a lesson which should echo throughout all deterministic and random scientific disciplines. Whenever the researcher attempts to formulate whatever formula, law, rule, or theory from a set of physical and experimental data. I think it's very important. Yo pienso es muy importante. Entonces yo púselo también en español. Hay una moraleja genérica y muy valiosa que aprender de la historia del éxito y el fracaso de la ley de Bode. Una moraleja que debería resonar en todas las disciplinas científicas, deterministas y aleatorias, siempre que el investigador intende formular cualquier fórmula, ley, regla o teoría a partir de un conjunto de datos físicos o experimentales. con cuidado, porque no es, it's not fitting the data into a formula. You need to think of the physics behind it. Fitting a formula into a data set is not good enough. It's not a guarantee of success. Tenemos 2-3 minutos más, entonces voy a cumplir todas las páginas. Kepler and Bode. John Kepler, age 25, es que yo estaba hablando del éxito del Kepler, pero no del fracaso, pero él tiene un fracaso antes. He had a failure. Kepler tiene a failure, a mistake, an error, un equivocado. De edad de 25, Kepler estaba preguntando la misma pregunta que Bode. John Kepler, age 25, also asked the same question Bode asked about the distances. While teaching an astronomy class in 1595, long time ago, Kepler had drawn his students the circumscribed and inscribed circles for an equilateral triangle. Equilateral is perfect, very symmetric. Circunscrito y inscrito. Bueno, one is big, one is small. Kepler was teaching his students that the ratio of the inner radius to the outer radius is 1/2. So the small one divided by the big one, the radius is 1/2. Exactly. Always. Doesn't matter what. It's a equilateral triangle is perfect. Suddenly, this is the scientist's mind, the mind of mathematician and scientist. Suddenly, Kepler connected in his mind this geometrical fact and the astronomical fact that the ratio of Mercury radius to Venus radius is 0.537. Ooh, interesting. 0.5, almost 0.5. Let's continue. Vamos a seguir. Tenemos un cuadrado, square es cuadrado, inscrito, circunscrito is different, is 0.707. Well, okay, so now Kepler is trying hard to fit the planets into perfect triangle, perfect square, perfect pentagon, perfect, symmetrical. But it doesn't work. Él no pude. Entonces, pero no, Kepler persisted. No paro, sigue. He didn't stop, he's trying harder. So he said, the world is, he had an idea, superior idea. The world is three-dimensional, as instead of applying polygons, figures in two-dimensional plane, let's use symmetrical solids in three-dimensional space. In the Greeks, hace 200, 500 años, the elements by Euclid, existe solo cinco sólidos, que son perfectos, simétricos, perfectos, pero solo no hay más. Ahora vamos a poner dentro de esto, entre spheres, entre ellos. Y sí, pude. Kepler thought, wow, Big es un éxito grande, míralo. Well, not so convincing. But he was very excited. Kepler was very enthusiastic about this approximate fit. So in 1595, at the age of 26, he published his book. But this is why Tycho Brahe invited him to Prague, because it was the little things that he did, and he was a little famous, and that's why he was invited to Prague, and that's why we had the advance and progress in physics, because he discovered the three laws. So it was good. It was a mistake. But the whole idea was in error. Era un equivocado. Un error. The book made Kepler a bit famous at such a young age, and that is the reason why he was invited to Prague by Tycho Brahe. He was beneficial to science. Kepler beneficial failure. Kepler model was later entirely disproved. Uranus and Newton, no hay más sólidos perfectos. No hay más. But Kepler's imaginative approach in borrowing from geometry, shapes, and results in order to model the solar system was highly creative. Es una gran idea. No one has ever even remotely performed a synthesis of such nature before, either in astronomy or in a scientific field. Él era el primer persona que toma cosas de geometría, aplicar a data en astronomía. Pero era error, sí, era equivocado. Pero la idea, el pensamiento, la forma que nos prestamos ideas de geometría a astronomía es grande, es muy interesante. In many ways, Kepler's failure attempt represents a turning point in the way astronomy and science in general would be done in the future, as it aimed to provide explanation behind what had previously been described science. And last, final point, la última cosa. Seldom in history has so wrong an idea been so seminal in directing the future course of science. Un error grande, pero era ¿cómo se dice? Una raíz para seguir adelante y tener mucho progreso. This is the lecturer, Alex, this is the book, and this is the end. Ahora, tiempo para preguntar. Gracias. Muchas gracias. Ahora es el tiempo duro para mí, tengo mucho miedo, estoy nervioso por las preguntas duras de los profesores y de los estudiantes. Espero que voy a sobrevivir esta experiencia esta noche. Vamos a ver. I hope I survive the questions from you.
Ya veremos, bien. Entonces, ¿preguntas? ¿Listo?
Sí.
Entonces, ¿por orden de estatura?
Bueno, buenas noches, muchas gracias por la charla, muy interesante. Y yo lo que quería era como que, me sonó lo que usted dijo acerca de que los griegos, digamos que no, el aporte no fue tan sustancial en cuanto a ciencia, contrario a lo que muchas veces se afirma. Y pues a mí me gustaría que de pronto profundizara un poquito porque, pues, por ejemplo, la medición de la curvatura terrestre, eso se hizo, o el diámetro de la Tierra, lo hizo Eratóstenes, y utilizando geometría, pero igual eran principios científicos sobre los cuales se estaba construyendo, ¿no? Ok, sorry. No, sorry. I was thinking about what you said related with the Greeks, so the contributions of Greeks to science. And
Yes.
I would say that it's not really few things that the Greeks did for science.
I agree.
And
Yeah.
for instance, Eratosthenes, who made the calculation for the diameter of Earth. So
Of the Earth,
it's
of the Earth?
And it's an example of applied science. For
Yeah,
instance.
that it was science, correct. You're right. So he made a hole in the ground in Egypt. I think it was in Egypt, actually, Greek Egypt. And he looked at the sun and the angle and the way it was down, and he calculated the diameter of the Earth, the radius or diameter of the Earth. Yeah, that is scientific. But that was a bit rare. It wasn't. They didn't continue with like, okay, taking like Galileo, dropping things, measuring, pendulum, looking at projectile motion. So yeah, it was science. That was really pure science, but it was a bit rare for the Greeks. The Greeks liked geometry, abstract, prime numbers. Can you touch a prime number? Can you eat a prime number? No. Can you see the prime number? It's an abstraction, yes. Can you see a triangle? Yeah, I can see examples of triangle and squares and the laws of geometry. But it was still not, we needed the Greeks. I agree with you, they were amazing. There's just no other nation on earth that did what they did in geometry, especially in geometry, philosophy too. But they didn't push forward to the next step. And that's what Galileo and Kepler did, and then Newton synthesize them. And that kind of humanity had to wait patiently until the Renaissance came. There was maybe a plan to wait, to start with the Greeks and have the Dark Ages, and then the Arabs, the Muslims, conserving the knowledge in Arabic, giving it back to Europe, etc. Yeah, I agree with you. But it wasn't rare. There was an interesting experiment. It's really purely scientific Greek experiment with the diameter. That's perfect. But not more examples of that. Not more. That was missing. Any other question?
¿Contento o...? Ok.
No quiero ofender a los grecos, no, no, nunca. Tengo mucho respeto a los grecos, mucho.
Dear Dr. Alex, thank you very much for your conference.
You're
I like
welcome.
this. I have the question. I will capture example, Earth on Mars. Yeah. The eccentric value applying the orbit, the planet orbit, that in Mars, in case of Mars, this value is more pronounced than Earth. In this case, Mars is 0.099, and the Earth is in the 0.017 or 0.017.
Softer, más suave, yes.
Yes.
Softer.
Yes. The question is, how could this value, the eccentric value in the orbit, modify the centrifugal force on the orbital on Mars than Earth?
Okay, very simple, because this helps you, the second law of Kepler is this. Hold on a second. The second law. Control.
Urian equality and time equality, the second Kepler law?
The second law tells you that you are speeding up next to the sun and you are slowing down farther away. So, in that case, a ver. Vamos a ver. Eso. So, on Earth, we are not speeding up and slowing down almost, because the sun is near the center of the physical circle. I know it's an ellipse, but it's almost like a circle. But on Mars, you're speeding up, slowing down. Speeding up, slowing down. Now on Mercury, you know that Mercury has more eccentricity. It's more, not like Mars, it's even more. So it's speeding up, slowing down. You can just imagine if this is the sun, and I am not Mars, Venus. Speeding up? No, sorry. Speeding up, slowing down. Speeding up, slowing down. Speeding up, slowing down. And that was the first clue of Albert Einstein in general relativity. As soon as he formulated the formulas of general relativity, the confirmation was Mercury. Because there's a difference between classical mechanics of Isaac Newton and general relativity of Albert Einstein, because of the high eccentricity of Mercury, which was known. And he immediately calculated, and his heart was jumping fast, beating fast, because it was correct. There was a discrepancy between the Mercury of Isaac Newton classic mechanics, and it was necessary to get general relativity to explain the data. It was real data of Mercury. And as I understand, because I read it, I haven't verified it. I have to trust. Tengo que tener fe. Pero dice que esa era la historia ya del 1915. Segundo año de la guerra primer mundo mundial. Para nada, una guerra para nada. Pero esta era, sí. ¿Está bien? Sí.
Yes.
Entonces, speeding up and slowing down. for Earth, we don't speed up and slow down. It's boring, muy aburrido. Siempre es como muy aburrido. Pero si vive o si usted vive en Mercury, es muy interesante. Es como, roller coaster, slowing down.
All the movement, no?
Yeah, the movement.
Around
So
the
if
sun.
you live on Mercury, you're speeding up. If you can sense that, we don't sense the movement of the planet around the Earth. We don't. But if you could somehow, you will see you're speeding up and then slowing down, speeding up and slowing down. Thank you.
Thank you.
You're welcome.
Hi. This one is more about your perception, but do you think that the actual physics or the actual science would have been so much better if all those errors or stuff that stopped the physics or the science to evolution through the history wouldn't have happened? Or do you think that the physics are like good as they are right now?
No, but you see, if you're going to get married and have a little boy, the little boy will start walking and fall down, and he'll start walking and fall down, and he'll learn. And finally he will walk. And one day he'll play football in Javiera. He will be a very good footballer. But how does the boy start? 1 year you start walking. How do you walk? You try and fall. You try and fall. Okay, you try and fall. You learn to speak later because to speak is mental. It takes more time, 1 year and a half. But you walk before you talk. So you walk 1 year, I think, about the babies, they walk 1 year. And 1 year and a half, they start talking. It takes more energy, more effort. But the failures are necessary, you know, the failures. For example, Kepler failure to look for the symmetric, perfect Greek solids is all false. It's an error, it's a mistake. But that was beneficial. This is how you connect geometry to real world. But not in this case, but later, yes. Later, for example, ellipse, it's from geometry, describing the motion of the planets. That's correct. Is that okay? So yes, beneficial, but we always make mistakes. It's necessary. And when you learn the language, you first speaking correctly, and then you improve, you practice. Practice makes perfect, la práctica hace al maestro, and then you learn. So it's the same, I guess, in science, or a little boy trying to walk and falling down. Thank you.
Thanks to you.
Thank you.
Hi. Well, my question for you is, how do you think that the existence of flat earthers and other models of the area affected the evolution of science?
Sorry, say that again, but a little more slowly.
Okay,
Yeah.
sorry for it.
Yeah.
How do you think that the existence of flat earthers
Of
and other
what? Existence of what?
flat earthers, the flat theory?
Oh, flat Earth.
Yeah, I searched
I
it.
think it's flat. This is flat. This is flat. I don't see anything round. It's flat, but it's not flat. Flat Earth?
Apparently, that's what it's called. Apparently.
Flat Earth is like people who talk about flat Earth. I think they're
Exactly.
wasting their time.
I know, but that's something you
Flat
said.
Earth. I don't know. But I think the flat Earth is okay. It's good because having skepticism and analysis is good. It's good. You say, well, the Earth is round. Other people say, no, Earth is flat. It's good in a sense. It's beneficial to make questions and to force the answer. But we know that the Earth is not flat. And we don't fall off. If you go to Brazil or Alaska or Canada or Russia, you don't fall off, boom, before that. But, okay, the idea to talk about flat Earth is good because it's provoking you. Don't listen to everything people tell you. Think, question, analyze, have skepticism. Skepticism is healthy. Intellectually is healthy. But you can say, you can have skepticism. The sun doesn't exist. The sun is an illusion. You can say the sun is an illusion. Okay, but so it doesn't help us much in thinking about the flat Earth. But it's good to ask questions and not to believe everything where you listen. If the television is telling you something, o El Tiempo, I don't know, what is the newspaper in Colombia? El Tiempo. Y si El Tiempo escribe algo, pregúntalo, como Flat Earth, pregúntalo, porque pues es una mentira. Maybe the television program is not true, so it's good. I like that in that sense. It's okay?
Okay, here we have some questions via YouTube.
Oh, okay.
The
Let me
first one
see.
was-
I don't know if I cannot access, but you tell me, Professor.
Juan Mejia is asking,
Yes.
do you think, what is this? Okay. Do you think religion has affected science in a positive or negative way?
Repeat, I'm sorry, repeat, Professor
Do you think
Alfonso.
religion has affected science in a positive or a negative way? Why?
But what was the first word? Do you think that what was the thing?
Religion.
Oh, religion. Religion, in a way, religion is science, because religion is asking about the existence, about the world, who created the world, how was the world created. So if you talk about religion, it's like, okay, today they say evolution, the Big Bang. I don't know, the Big Bang 14 billion years ago. To me, that sounds like a very big conjecture. In other words, okay, if I need to believe in a Big Bang 14 billion years ago, and then the evolution coming and creating us, molecules, heat in the ocean, so the religion in a way is science, okay? Because it's asking about the world, the existence of the world, how the world came to be, who created the world, okay? So science will say Big Bang, evolution. From molecules, you get the DNA. From molecules, the heat of the ocean, and then you duplicate, and then you have natural selection. I don't know, but the Big Bang, for me, is a little bit suspicious. But religion, ultimately religion is different, because religion has a moral things. Don't kill, the 10 Commandments, los 10 mandamentos, gracias, los 10 mandamentos, don't kill, don't steal, etc. So it has a moral issue, and it has also the question of the meaning of life, and the meaning of life you cannot answer by science. It's very hard. I don't believe you can answer by science. Okay, so I hope the guy from the questions in the YouTube is satisfied, but I'm not an expert in religion or theology so much, but I try my best.
We have to hurry up a little bit because we have many questions here.
Okay, should I go up or should I stay here? Okay, speak louder if you can. Habla alto, como se podría escuchar ustedes.
Okay, I got a question. So, if the variables of a planet are actually random, or maybe they follow a random path, is there any econometric model to estimate these values, or have anyone tried it?
Sorry, I didn't understand. Maybe you speak a little more slowly, because a little more slowly, more clearly, more slowly. O en español, y profesor Alfonso va a decir, como desea, como sea. Por inglés muy despacio, muy claro, por favor.
So, if the planets have actually random variables, have anyone tried values?
If the planets what? If the planets what?
Have random variables or values?
Have what? Values?
Values.
Oh, random values. Yeah, definitely. Random. I believe it's random.
So, have anyone tried to use an econometric model to try to estimate these values? Or at least
como statistical models to evaluate it? Econometric model. It's interesting question. But you remember, let me ask you, interesting question. No, I think, no, after Kepler and after Bode especially, they gave up on it. I think they gave up on it. But
But if you look, let's look again. You question? Let's look again. Look at the, I'm taking the data of the, you're talking about the distances, right? Las distancias, ¿sí o no? ¿Sí o no? Las distancias. Look at them on the logarithmic scale. It's not perfect, but it looks reasonable. Es razonable. Es razonable. Ahora, pues hay una planeta aquí, no sé, pero pues, si tenemos unos planetas aquí en X logaritmo, es un problema, es feo. No sé, pues, but yo no sé, yo no puedo contestar. I cannot answer your question, but I think that after the failure of Kepler, and especially after the failure of Bode, they didn't want to touch that. They say the planets are random. I don't look any model, statistical model, regression, logistic, I don't know. It is random. Remember that as you move around the star, things tends to glue the gravity. You can't have two planets together. So this is now together, but if this is bigger, it will eat this. It will be one planet. But only the distance let them stay alive. So don't eat me, I'm too far, so you're too far, don't eat me. This planet, don't eat this planet because you're too far, your gravity is weak, it's okay, I can exist. Don't bother me. But if you're very near, you swallow up. You need, so the distances between the planet is a physical law, is a physical law of gravity. You cannot have to each other, so you need a little distance. But there is a distance. So the Earth cannot eat Venus and Venus cannot eat Earth because the distance, remember, the universal gravitation of Isaac Newton is G m1 m2 divided by r squared. And that's like r squared, so as you go far away, it becomes very weak. I cannot touch you. That's why. Is that okay? Does that answer it? I don't know, but I think nobody dared to go into the topic again. They got scared. It's two failures, Kepler and Bode. So just leave it like that. It's random. Leave it like that. It's random. Okay. Any more questions? Yes.
Okay, so this is our question, and it is
joint question together. Yes.
So, which reference system do you think Isaac Newton and all the other scientists used to create all of the contributions, ideas, and thoughts regarding that the solar system or the Earth is in constant movement?
Oh, you mean the movement of planets or the solar system itself in the galaxy? You mean the solar system in the galaxy or the planets within the solar system?
Both of them.
Both. Okay, so first of all, Isaac Newton, compared to the other scientists, this was a multi-generation project between 6 scientists. Only Galileo and Kepler were contemporary. They lived almost at the same time, and they knew each other. They wrote letters to each other. They supported each other because Galileo was passionate about the geocentric model, and Kepler was even more passionate about the geocentric model, and they supported each other, and they were both afraid of the Inquisition at the time. But the other ones were a different generation. They knew each other through the books written in Latin, and they continued the work. But it was an intergenerational project of about 150 years, 170 years, and the fact that the motion of the planets within the solar system, of course, Isaac Newton understood that if you have somebody big and stop them for one moment, it's somebody huge, big, some animal or some kind of something that will stop the planet for one moment, they will fall to the sun. But somebody or something gave them a push in the beginning, not too strong, not too slow. Too slow, you fall down. Too strong, you fly off. And so Isaac Newton could not tell you who started the process. But there was a sun and pieces of dust and things forming around, and they got the energy, the push to move. Okay? So, for example, if I go to the top mountain in Colombia, what is the biggest mountain in Colombia? The Sierra Nevada. And I take a gun, a strong gun, and I shoot straight. If I shoot too slow with not so much power, it would fall down to Colombia. If I shoot stronger, it will go down maybe to Canada. But if I shoot just right, it will go around and around and around. If I shoot too fast, too strong, it will go in space and never come back. All right? So if you have a gun or a cannon, I think of a cannon, artillery, military artillery on the top, perfectly horizontal. Depends on the speed, the power, what will happen in the future. If the speed is slow, it will fall down. If the speed is faster, it will go to Mexico. If it's more, it will go to USA, then Canada. If it's more and perfect, it will keep on going forever, Perpetual motion machine. I don't need gasoline, I don't need gas, I don't need energy, I don't need an engine. But if you shoot too much, it will be like a missile going to Mars or going to space and disappear and gone. The solar, now about the Milky Way galaxy, I think Isaac Newton never got to that. At that time, it was not clear, it was not known, the galaxy. It was enough to deal with the solar system. He wasn't dealing. It's okay? Okay. Any more questions, students? But I have energy, Professor, I have energy. I can stay longer. I'm not tired. Only, okay. You do it, okay. Question?
So, Alex,
yes.
In first place, thank you very much for your presentation. I think it was
Yes.
pretty interesting.
Thank you.
And I think my question is a little ambitious, but I'm curious to know your opinion, taking into account that you are a little bit more, I don't know, like deeper in those themes you exposed. And it is, we know maybe like the first scientific developments, in quotes, are in the times of the Greeks, that it's before Christ. But yes. When really the scientific developments settled in society was in the Renaissance. The Renaissance is in the 1500s, so that period of time is pretty big from the time before Christ to the Renaissance.
Yeah, interesting, very interesting, yes.
So my question is, how would you think it would be the science development right now if those same science developments were maybe settled in the time of the Greeks? I mean, those things we...
Earlier, before, más temprano?
Yes, that.
Pues muy peligrosos. Because the power of science is bombs, nuclear weapon. I don't know about nuclear weapons. I'm not so scared, but chemical bombs, poison, biological warfare. You look at the world, so many wars, so many conflicts. Only in Colombia you have civil war, and now you have in Ukraine, in Russia, in Iraq, in Iran, in so many wars. So I think maybe we are blessed. Ignorance is bliss. But to be ignorant sometimes is good, because the bad guys can use science to create weapons and to create terrible things. Because every society in history, we know that history is dangerous. We are lucky to be alive. We live in a good time, actually. But if you lived in the Middle Ages in Europe, you have army coming, soldiers killing you, stealing your food. We live in a good society, but we know that it could turn around and could be bad. So maybe it's good that science came later. Maybe it's very good. I don't know.
Okay.
Yes.
Entonces agradezcámosle a Alex, al profe Alex, su charla. Y bien, este es el aperitivo para noviembre 24. No, el simposio es noviembre. Es que el simposio que vamos a hacer al final, queda una charla más, el simposio va a ser sobre el sistema solar. Entonces vamos a tener al menos 2 charlas técnicas astronómicas sobre el sistema solar muy, muy lindas, divulgativas, y otro par de cositas. Entonces esta es como la introducción al simposio y nos queda todavía una charla noviembre 3.
Eso. Thank
Que
you
es
very
sobre
much.
astrobiología.
Very nice lecture. Thank you. You are with your house here, the Zion Bank. 3 de noviembre tenemos nuestro próximo coloquio. Están todos cordialmente invitados. El tema es astrobiología. Astrobiología. Viene un profesor que se llama Jorge Bueno. Él tiene algunos proyectos en torno a esto de la astrobiología. Entonces, también nuestro próximo coloquio. Agradecerle entonces a la Facultad de Ciencias, que el año pasado estábamos cumpliendo 50 años de creación. A la Facultad de Teología, que este año está cumpliendo 85 años de la creación, y a la Facultad de Filosofía, que está cumpliendo 100 años de la creación del doctorado en filosofía. Entonces, ojalá que nos puedan acompañar el 3 de noviembre en 20 días, y como estaba diciendo Alfonso, tenemos el jueves 24 de noviembre, en horas de la tarde, de 2 a 5, nuestro simposio. Vamos a tener 3 invitados en torno al tema del sistema solar.
Y con eso sí cerramos el año en torno a las actividades académicas, ¿no?
Entonces, muchas gracias
Muchas
por su
gracias,
asistencia. Nuevamente un aplauso para Alex. Y
Gracias. I just want to say that I will ask the professor to send each one of you through email the file, the PowerPoint file, that you can look at it one more time and look at it at home at your leisure time. Voy a enviar este archivo del PowerPoint para ustedes todos en correo electrónico para revisar y para disfrutar si quieres verlo. Gracias, gracias a usted.
Gracias a todos, sin ustedes esto no es posible.